Okay, welcome back, physics fans. Here we are doing number 14 on the momentum and impulse worksheet. The momentum on impulse worksheet number 14. Sami is skating with the puck that has a mass, so this mass is going to be 0.320 kilograms. Okay, and the initial speed that he's traveling at is 14 meters per second. And then he unleashes a slap shot. He smacks the puck and it screams towards the net at 50 meters per second. So the final velocity after the smack is 50 meters per second. Calculate the change in momentum. So the change in momentum is mass times the change in velocity. And the mass of this is 0.320 kilograms. And the velocity of that, the change in velocity is final minus initial. So the final minus initial, final is 50 meters per second, and the initial is 14 meters per second. So when we pull up Mr. Calculator here and go 50 minus 14, the change in velocity is 36, and multiply that by 0.32, we get 11.52 units, kilograms, times meters per second. And if it needs a direction, we'll just go forward or away from Sami towards the net. Okay, next, B, let's change the color here. Let's do B right now. If the puck was on the stick for 1/100th of a second, so the time, we're adding one more thing on there, the time of impact with the stick, not very long, calculate the force that the stick was exerting on that. So the formula that we're trying to use here is that impulse is equal to the change in momentum. And impulse is force times the change in time, or just time by itself. You don't have to have the change in time. And it's equal to the change in momentum, which we already have, which is 11.52 kilograms meters per second forward. So that's just going to give us the force is equal to 11.52 kilograms meters per second divided by the time, which is 0.01 seconds. Mr. Calculator comes up and divide this by 0.01, and we get 1,152 newtons forward. So that's a pretty good force. That's equivalent mass, if you had to do it for a force of gravity, would be like 117 kilogram mass. That's the force of gravity. That's the force of impact that he was doing on that. But not for long, 100th of a second. Then C, here we go. Here's the concept and the practice. What impulse did the stick experience due to its collision with the puck? So we're now asking for what is the impulse on the stick. What is the impulse on the stick? Well, the stick came down, there's the stick, and it hit the puck. But if it hit the puck this way, then the puck hit back on the stick that way, Newton's third law. And the time of impact here would also be the time of impact there, the time pushing back. So we could just say, from Newton's third law, force on stick equals negative force on puck. And times about the time for both the impact are the same. Therefore, impulses would be same but opposite. So in other words, if we're trying to use last chapter's information, we would then go that the impulse on the stick, impulse on stick is going to then equal negative the impulse on puck. And therefore, the impulse is going to be negative 11.52 kilograms, not kilograms, newton seconds forward. But negative forward just would mean one 11.52 newton seconds backwards. I'm trying to explain it all with Newton's second law, but that's not what we have to do in this chapter. But I'm doing it. There's our answer. But how could have we done this without going to Newton's third law and using that the time concepts are the same? So that means the force times the time here has to equal negative the force times the time here, and came up with impulse is equal to negative impulse, and then did it this logical way, because this was the change in momentum, which is also the impulse. But the way to do it, if you were not going to use Newton's laws, is use the conservation. Of momentum. That the momentum before has to equal the momentum after the collision. There's a collision happening here, but that means the change in the momentum of the puck plus the change in the momentum of the stick would have to equal 0. There cannot be a total change in momentum because momentum is conserved. So if this is going to be positive 11, then this has to be negative 11. Okay? And that would have been the perfect argument instead of going these 3 steps and then showing the calculations, is to show that, hey, it's a conservation of momentum, so the increase in momentum of one object has to be the decrease in momentum of the other. So you would say if this is 11.52 newton seconds forward, then the other one has to be negative 11.52 newton seconds forward, so that just backwards. That's it. Any questions?